In example 2, we're given a function with no domain restrictions. It's a polynomial function, so it's continuous everywhere. Since we have no domain restrictions, what we're going to do is start off by finding any local extrema, and then see if we can also determine that any of those local extrema are also absolute extrema. So we'll start off by finding the first derivative of our given function, which in this case will be 2x minus 8. Setting that equal to 0 to find any critical values will give us a result of x equals 4. So we know that if we evaluated our first derivative at 4, we would get 0. So the next thing to do is find the second derivative of our given function. So taking the derivative of the derivative, we would get 2. Our second derivative evaluated at 4 then would be 2, since there is no x variable in there. So that's going to be positive for any value. So in this case what we have is a function that's concave up. So we have our first derivative equal to 0 at x equals 4, and our function is concave up, which means x equals 4 is a local minimum. We have no points to consider as an absolute maximum, only the single critical value. But what we do need to know for sure is if this is a local minimum or an absolute minimum. So to consider that, we can consider the limit of our function as x approaches infinity. So thinking back to our limit problems, if we're considering the limit as x goes to either positive or negative infinity, the only thing that matters is just that dominant term, so the term with the highest power. So this is going to be the same thing as the limit as x goes to infinity of x squared, which in this case will head to positive infinity. We also need to consider the limit as x approaches negative infinity of x squared. So we're plugging in negative numbers, but squaring them so they're becoming positive. So this is also headed to positive infinity. So since we get positive infinity, there is going to be no absolute maximum, but we don't have the end behavior headed to negative infinity. So since in neither direction are we headed to negative infinity, that means we have an absolute minimum at f of 4. So x equals 4 was a local minimum. Since neither of the end behaviors go to negative infinity, now we can classify it as an absolute minimum, which will occur at f of 4, and plugging that back into the original function, our absolute minimum will occur at negative 13, or at a function value of negative 13. In example 3, we have a similar start, no domain. So we start off by finding the derivative of our given function, which in this case will be 3x squared plus 6, and then set that equal to 0. So solving for x squared, we would subtract 6 over and then divide by 3, which gives us x squared equals negative 2. In order for that to be true, x would have to be equal to plus or minus the square root of negative 2, so we would take the square root of both sides to cancel out that exponent. But we can't take the square root of negative numbers, so x can never be equal to plus or minus square root negative 2, so our first derivative function can never be equal to 0. Since we have no critical values to consider, that means there are no absolute extrema. So if we can't find any points where the first derivative is equal to 0 or undefined, there are no critical values to consider, and we just conclude that there are no absolute extrema for that function. So similarly in example 4, we'll start off by finding the first derivative of our function, which in this case will be 36x squared minus 36x cubed. We can factor out 36x squared, leaving us with 1 minus x. Setting that equal to 0 gives us two values for x to consider. We get both 0 and positive 1. So then considering the second derivative of our function, we'll take the derivative of the derivative to get 72x minus 108 x squared. So we have the second derivative, so using the second derivative test, we can evaluate the second derivative at 1. So plugging in 1, we would get negative 36 into our second derivative. That result is less than 0, meaning that at this point our function is concave down. So if our function is concave down, that means we have a local maximum occurring. Using the second derivative test again, in this case on our other critical value of 0, plugging in 0 to the second derivative gives us a result of 0, which is inconclusive. So we need to consider a sign chart for f prime for the first derivative. So we know we have critical values at 0 and at 1. Since the second derivative test was inconclusive, we need to look at using the sign chart. So we're going back to a first derivative test. We already know that x equals 1 is a local maximum. So the behavior of our function should be that it changes from increasing to decreasing, because that would give us that behavior for a local maximum. So we only need to look at choosing a test point below 0. So for instance, negative 1. Plugging in a value of negative 1 into our first derivative will give us a positive result, which means that at 0, our function doesn't change directions. So x equals 0 is neither a local maximum nor a local minimum. So we only have one point to consider, x equals 1, and we need to determine if that's also an absolute maximum. So to do that, we'll consider the limit as x goes to infinity of our original function. But again, we only need to consider the dominant term, which in this case is negative 9x to the fourth. We're taking positive values, plugging them in for x. So x to the fourth is getting larger and larger, but then we're multiplying it by a negative 9. So this is actually going to be headed to negative infinity. We'll consider the same thing for x approaching negative infinity. So we're plugging negative numbers in for x, but taking those to the fourth power, making it positive, so that's going to get larger and larger. But again, multiplied by a negative number gives us negative infinity. So the negative infinities tell us there's no absolute minimum, but since neither of these are headed to positive infinity, that means our function is going to take on its largest value at this local maximum, meaning we have an absolute maximum. At h of 1, and that function value there would be 3. And just really quickly, let me go back for a second here. That should have been a sign chart for h prime, not f prime. So we identify critical values, look at either using the first or second derivative test to classify those as local extrema. Then we consider the end behavior to see if our function at its extremes ever exceeds this function value. In this case, it doesn't, so we have an absolute maximum.